Hi, I'm Lakshmi, and I worked on this project with Anwesa, Swapnendu, and Zakar. And our final project is called Comparison of Graph Traversal Algorithms in Web Crawling. So this PowerPoint is basically going to give you an introduction on our project and a background context on web crawlers, and we'll explain the different graph traversal algorithms we used with web crawlers and the observation and analysis on our results, and finally the conclusion. So to give you a little introduction on our project, we are basically doing a comparative analysis on different graph traversal algorithms and how they perform in web crawlers based on different situations. And to do our analysis, we use different search algorithms. So some of them are breadth first search, depth first search, depth limited search, iterative deepening search, and the greedy search. So a web crawler is basically like a search engine bot, and it's used to download and index context around the world. So the goal of a crawler is basically to learn about every single web page that's on the web. And it is used by many different search engines to basically provide the relevant links that a user is trying to search for. So for example, if I'm going on Google and I search for a certain type of thing, then a web crawler is used to get all the data that it's stored before to give me the relevant links based on my search. So the first graph traversal algorithm we'll talk about is the breadth first search. So the breadth first search is an algorithm that is used to search a tree or a graph, and it usually is there to find a node that meets the given criteria. And it begins with the root node of the tree or the graph and looks at all the different nodes at the current depth level before moving on to the nodes at the next depth level. And the time complexity for BFS is big O, V plus E, where V is for vertices and E is for edges. And in our implementation, we leveraged BFS to implement a web crawler. So we pass a seed URL as our root node and perform BFS by traversing all its child URLs every level wise. And we also pass a target URL to check if this target URL will be found or not using BFS. And we provided a maximum depth. So BFS will basically only run until this depth is reached. So a drawback that comes with BFS is that if a URL ever resides in like a much deeper level, then it'll take a lot longer to find this URL, or it also has a chance of not ever finding it because we have a max depth that we have in our code.
Hi, my name is Swapnendu, and today I'll be discussing the other algorithms that have been used in the implementation in our project. So alongside the breadth first search as discussed by Lakshmi, we have also looked at a few depth focused algorithms like the depth first search, the depth limited search, and the iterative deepening search. And we've also taken a look at the greedy search. So we'll basically take a brief look at these algorithms and how we've implemented them in our program. So starting off with the depth first search, we know that the depth first search is a fairly common algorithm where the search process begins at the root node and gradually we progress down a single branch till the end of the branch towards the leaf nodes, following which if we do not find the goal node, then we progress to the next branch. So the time complexity of our depth first search is known to be O of V plus E, where V is the number of vertices and E is the number of edges. For our implementation of a depth first search, we have maintained like same process, the same code as that as the BFS, but the only change that we made was in the data structure used. In case of BFS, we used a queue, but in case of depth first search, we had to use a stack. So some of the known drawbacks of depth first search is that once looking for the goal node, if the goal node resides in the upper level, but in the branch far away from the beginning, then depth first search might take a long time to reach there since it has to traverse through all of the branches before that. Also, subsequently, a depth first search might get stuck in loops in certain cases, and in which case it might not be able to find the target URL or the node in question. In order to solve these drawbacks, we'll take a look at the next algorithms. So the depth limited search is a special case of the depth first search where we can set a predetermined depth limit in order to stop the algorithm from running into a rabbit hole while searching along a particular branch. So this way we can make sure that we take a look at multiple branches before progressing further down, and this gives the depth limited search a functionality which can be called a combination of both the breadth first search as well as the depth first search. So the time complexity of the DLS is known to be O of B to the power L, where B is the branching factor and L is the given depth limit. So as for the implementation, we have used a hash map where we stored the nodes as a key and the level as the values. By doing this, we could find the level of each of the URLs and make sure the traversal is limited to only a certain maximum level. It is possible that if we set a level, the URL that or the goal node that we're looking for might not exist within that particular level, in which case we will have to progressively increase the level and try again. That is all about the DLS. We will now take a look at the iterative deepening search. So the iterative deepening search can be considered as a special case of the depth limited search of the DLS, which we just had a look at, in the sense where we do not have to specify any particular depth or limit. The algorithm will gradually progress through a range of values, starting from the lowest possible value to the maximum value for the depth, and iterate through these values to find the optimum depth needed to come across the target URL or the goal node. So in that case, it takes advantage of the completeness of the breadth first search strategy, and alongside that, it also uses much less memory in each iteration, like the depth first search approach. So the time complexity used by the iterative deepening search is known to be O of b to the power k, where b is the branching factor, and k is the depth where the solution is found. In case a solution is not found, k is the last depth, or the depth of the tree. So in our implementation of IDS, we have repeatedly iterated through the tree using the DLS method, which we have created for the previous algorithm. And the only known drawback to IDS is that it might have to repeat the computations, and unless it finds the goal node early, there might be some wasted calculations. So finally, we'll take a look at the greedy search. So a greedy algorithm is a very popular approach to solving similar problems, where the graph traversal is performed using the algorithm which decides on which node to traverse to at every transition based on a specified heuristic value, and it always tries to maximize its performance by choosing the best available option that is presented to it based on the provided heuristic values. The immediate best choice is always taken in the greedy choice, and in this case, we provided a heuristic in the form of the loading time of a page, and so the algorithm would look at all its available nodes and then make a choice based on the least loading time. So for our implementation, we had to write a separate function in order to calculate the heuristic, and another separate function to use the calculated heuristics to travel using the greedy search. One more thing that I would like to add is that in order to calculate the heuristics, we used a priority queue, where the calculated loading time of a page was then set as the priority, with the least loading time was set to be the page with the highest priority. That is all for the greedy search.
Hi, my name is Anwesa, and today I'm going to give you a presentation on our final algo project. Continuation from Swapnendu, I'm going to explain about the observation and analysis that we found based on several runtime comparisons and memory comparison on different scenarios. So till now we have known about different graph traversal algorithms and learned about their drawbacks and advantages. Now we're going to see that how they perform with each other and which is the most efficient algorithm. So we have performed 4 scenario based analysis. Let us go through those scenarios one by one. So in the first scenario, we can see that we try to find the most efficient algorithm when the target URL is at a deeper level of the graph. So in this scenario, we can see that from our result, BFS performs the worst. It took the most amount of time among all the algorithms, and it also crawled the most number of URLs. Even though it found the target URL, but it is the worst in terms of runtime performance. Whereas DFS and DLS performed pretty good. So the reason behind this is BFS performs level-wise traversal, so it completes each level and then it go into the depth of the graph. So since the target URL residing at the more deeper level, so BFS has to crawl more number of URLs, BFS has to expand more number of nodes until it reaches to that level. Whereas DFS and DLS doesn't have to traverse level-wise, and they doesn't have to crawl this many number of URLs. They can easily reach to that depth, and they can easily, once they get that node, and they can easily exit that operation. So because of that, they took lesser time. Even though IDS performed pretty good, but here IDS could not outnumber DLS because IDS is also iteratively calling DLS in each level. So from the graph also it is clearly visible that DLS is the best. In scenario 2, we have taken the exact opposite scenario from what we have done in scenario 1. We tried to find the most efficient algorithm when the target URL is in the upper level. In this case, BFS performed really better than DFS and DLS because of the similar reason that it found the URL way faster. Because suppose if the URL is in level 1, so since it will complete the level 1 first, it can easily find the URL way faster than DFS or DLS does, and it can terminate the program. Whereas DFS or DLS will go into depth and then it will backtrack and reach the level 1. So because of that, they has to crawl more number of URLs, they has to take more time. So here we can see that although BFS performs pretty good, so is Greedy, but IDS beats everybody because IDS is a combination of both BFS and DFS, and since we are iteratively traversing each level, then obviously IDS will find the node way faster than others, and it has to crawl the less number of URLs. So in the graph also it can be clearly seen. And finally we'll discuss about the scenario 3. Here we're going to find the most efficient algorithm where the target URL is in upper level, but it is in a sparse tree. So the target URL is residing in the upper level like scenario 2, but it is going to reside way farther from the root URL. So in this case, BFS will perform pretty good because BFS will do level-wise traversal. DFS and DLS will perform bad, and it is like the result is kind of similar to the scenario 2. Only difference that we can see is that here DFS will not be able to find the target URL because since it resides farthest from the root node, so it will exit all the maximum level limit, and because of that the program will be terminated. So here also we can see the most efficient algorithm is IDS, and which can be clearly seen in the graph as well. So yeah, that's it. Thank you.
In scenario 4, we asked the question of which algorithm is most efficient based on approximate memory usage. After running experiments to measure approximate memory usage, we identified that iterative depth search in the worst case had the best performance. Note that depth-focused algorithms, such as DFS, had stable performance, displaying a shark fin pattern in memory usage, whereas breadth-focused algorithms, such as BFS, displayed exponential memory usage. That said, an improvement to all algorithms to address the issue of exceeding available memory would be to use a database to store data on disk and access it as needed, thereby improving their use in web crawlers. For the comparative analysis, we created a chart to show the number of links visited per algorithm in each scenario. In scenario 1, we aimed to find a target URL at a deeper level of the graph and saw that breadth-focused algorithms visit many more links than depth-focused algorithms. In scenario 2, we aimed to find a target URL at an upper level of the graph and saw that breadth-focused algorithms visit fewer links than depth-focused algorithms. In scenario 3, we aimed to find a target URL on a sparse graph and saw that breadth-focused algorithms visit fewer links than depth-focused algorithms. In scenario 4, in the worst case, we measured approximate memory usage in traversing the graph and saw that depth-focused algorithms performed better than breadth-focused algorithms. To conclude, we implemented graph traversal algorithms and did a comparative analysis of each to identify which are most efficient in different scenarios. Based on our results, it is clear why such importance is placed on identifying the most efficient graph traversal algorithm for a particular problem, as demonstrated in the scenarios. Thank you for your time. We hope you enjoyed learning about graph traversal algorithms as much as we have.